Welcome back to AI.Code.Cast. You've been prepping for that big tech interview.
Yeah.
Well, we're diving into a coding problem that often pops up. Evaluate division.
Oh, yeah.
It's known for being a bit of a brain teaser.
Definitely.
Ready to unpack this one together.
Absolutely. It's a favorite among interviewers because it really tests how you think about data structures and algorithms.
Oh, yeah.
Not just whether you can memorize them.
All right, so imagine you're given a bunch of equations.
Okay.
Things like A, B, 2, that sort of thing.
Yeah.
Then you get a list of queries, like what's a C?
Right.
Your mission is to calculate those queries using only the info from those initial equations.
And there's a catch.
Oh.
If you can't figure out an answer based on what you've been given, you have to return minus 1.0.
Okay.
So if you only have equations relating A and B and someone asks about X, you're out of luck.
Okay, I'm seeing the puzzle pieces here.
Yeah.
We have to connect the dots between the equations to solve for the unknown ratios.
That's right.
Can we look at an example to make this more concrete?
Definitely. Let's take example 1 from your source material.
Okay.
We have equations like AB2, BC equals 3, and a few others.
Well,
one query asks for a C.
So, thinking like the interviewer, how would someone approach this without jumping into fancy algorithms right away?
Well, the most intuitive approach is to try and combine the equations directly.
Okay.
Do you see how we could get to a C using what we have?
Well, I see AB2 and BC equals 3.
Yeah.
If I multiply those two equations together, the B's cancel out, and I'm left with a C6.
Exactly. That's the brute force method.
Okay.
Manipulating the equations to get the desired ratio.
Yeah.
It works great for simple cases, and interviewers like to see that you understand this basic logic.
But I can already see how this could become a nightmare with a ton of equations.
Right.
Like, what if we had 20 equations with variables like M and P and so on?
Oh, yeah.
It'd be like trying to solve a massive Sudoku puzzle.
You're hitting on the key limitation of brute force.
Yeah.
It doesn't scale well.
Right.
It gets messy and inefficient really quickly.
So if I tried that in an interview,
Yeah.
I bet the interviewer would then ask, okay, that works, but how would you handle this with hundreds of equations?
Right. Absolutely. They'd be looking for you to bring in more sophisticated tools.
Yeah.
And that's where algorithms like graph search and union find come into play. They provide more systematic and efficient ways to handle these complex scenarios.
Okay, so brute force lays the groundwork.
Yeah.
But it's definitely not the final answer.
Right.
Let's explore these other approaches.
Okay.
Tell me, when you first encountered this problem,
Yeah.
which solution clicked for you first?
For me, it was the graph search approach.
Really?
It's very intuitive because it mirrors how we naturally solve the problem, connecting the dots. But before we dive into that, are there any other pitfalls someone might stumble into with the brute force method?
That's a good point.
Yeah.
I'm guessing one pitfall is not recognizing when a solution is impossible.
Absolutely.
Like if there's no way to connect the variables in the query
Right.
using the given equations.
Exactly. It's easy to get lost in the algebra and keep trying different combinations even when there's no solution.
Right.
A key skill is recognizing those dead ends and confidently saying, based on the information given, there's no way to calculate this.
Okay, so knowing when to stop is just as important as knowing how to proceed.
Yeah.
That's a good tip. So back to the graph search approach.
Okay.
You said it clicked for you because it's intuitive. Can you elaborate on that?
Sure. Think of each variable in our equations as a city on a map.
Okay.
Each equation represents a road connecting those cities, and the value of the equation is like the distance between them.
Okay. Well, I'm liking this visual already.
Yeah.
So our equations become a roadmap of sorts.
Right. And solving a query like a C becomes like finding a route from city A to city C on our map. The answer is then the total distance of that route.
So if we have AB2 and BC equal 3, it's like going from city A to city B with the distance of 2,
Right.
then from B to C with the distance of 3.
Exactly. The total distance would be 2 multiplied by 3, which is 6.
Right.
Giving us the answer to a C. Does that make sense? It's starting to click.
Yeah.
So instead of juggling equations, we're navigating a map.
Right.
But how do we actually find those routes efficiently?
Yeah?
Maps can be huge and have lots of dead ends.
That's where our old friend depth first search, DFS, comes in.
Oh, okay.
It's like a systematic explorer for our map.
Okay, so DFS is our navigation system. But I remember DFS from my algorithms class, and it can be a bit, well, deep.
Right.
How does it apply to this specific problem?
It's actually quite elegant.
Oh.
Imagine DFS starts at city A and tries every possible road leading out.
Okay.
If it reaches C,
Yeah.
great, we have our route.
Okay.
If not, it goes back and tries another road, and so on. So it's like a methodical detective
Yeah.
checking every possible path until it finds the right one.
That's a perfect way to put it.
Okay.
And just like a good detective, DFS keeps track of where it's already been so it doesn't waste time going in circles.
That's smart.
Yeah.
And that makes it efficient for solving this problem.
Right.
But before we get completely lost in the graph search forest, let's pause here.
Sounds good. Taking a moment to let those ideas settle is always a good idea.
Okay.
Plus, there's a lot more to explore.
Right.
We haven't even touched Union Find yet.
Exactly.
Yeah.
But I think we've laid a great foundation so far.
Yeah.
We've gone from the basic problem to the limitations of brute force, and now have a glimpse of how graphs and DFS can help us.
Yeah.
Ready to keep going.
Absolutely. Let's dive deeper into the specifics of graph search and then see what this Union Find thing is all about. So you're starting to see how we can transform this evaluate division problem into something more visual, something we can navigate like a map.
Right. It's way more appealing than shuffling equations around.
Yeah.
But I'm still a bit fuzzy on how we actually build this map using our equations.
Okay.
Can we walk through that step by step?
Absolutely. Let's stick with that example we were using.
Okay.
AB2, BC is 3.
Uh-huh.
And let's throw in CD4 just to spice things up a bit.
Okay, 3 equations, 4 variables. I'm ready to map this out.
Well, first, each variable gets its own node, like a city on our map.
Okay,
So we've got nodes for A, B, C, and D.
got it. 4 cities, all set.
Mm-hmm.
Now for the roads.
Yeah.
How do the equations become those connections?
Each equation gives us 2 roads,
Okay.
because division works both ways.
Oh, right.
Take ABE2.
Yeah.
That means there's a road from A to B with a distance of 2,
Uh-huh.
but also a road back from B to A.
Right. Because if A is twice B,
Yeah,
then B is half of A.
that's right.
So that return road would have a distance of 12.
Mm-hmm.
Got to keep track of those reciprocals.
Exactly. We do the same for the other equations.
Good.
BC Okros gives us roads between B and C with distances 3 and 13.
Yeah.
And CD4 connects C and D with distances 4 and 14.
Okay, picture coming together nicely.
Yeah.
4 cities, 6 roads, all with their distances marked.
Right.
Our equation roadmap is ready.
Now imagine we get the query AD using our graph.
Yeah.
The problem becomes find the route from city A to city D.
And that's where DFS comes in, right?
Yes.
Like a super efficient travel agent figuring out the best path.
Precisely. DFS would start at node A and systematically explore each connected road.
Okay.
Let's say it first tries the road to B.
It's at B now, not the destination yet.
Right.
What happens next?
DFS keeps track of the total distance traveled so far.
Okay.
Since it went from A to B,
Okay, yeah.
the distance is currently 2 bly.
Okay.
Now from B,
Yeah.
it has 2 choices. Go to
Yeah.
A or go to C.
Well, going back to A would be silly. It'd be going in circles.
Yeah.
So it must take the road to C,
Right.
adding another 3 to the total distance.
Exactly. Now it's at C with the total distance of 5 and sees the road to D. It takes that final road, adding 4 to the distance,
Okay.
and bam,
Yeah.
it's reached the destination.
So the total distance is 9.
Yeah.
Meaning a D equal 9 according to our graph.
Exactly.
That's so cool how it breaks down each step.
And notice how DFS was methodical.
Right.
It didn't randomly jump around the map.
Yeah.
It explored each path fully before backtracking.
That makes it more efficient.
Mm-hmm.
But I'm guessing there's a trick to make sure DFS doesn't get stuck in loops, right?
Yeah.
Like what if there was a road back from DD?
You're thinking like a true algorithm designer.
Yeah.
Yes, to prevent infinite loops.
Okay.
DFS uses a little helper, a way to mark cities as visited.
So it's like leaving breadcrumbs to remember where it's already been.
Perfect analogy.
Yeah.
Once DFS leaves a city, it marks it as visited.
Okay.
If it ever comes back to that city.
Yeah.
It knows it's already explored all paths from there and moves on.
That's so clever. Okay, I'm really liking this graph search method.
Good.
But you mentioned another approach, Union Find.
Right.
That name sounds intimidating, to be honest.
It does sound a bit abstract.
Yeah.
But it's actually quite elegant once you get the hang of it.
Okay.
It's based on the idea of grouping variables together based on the relationships in the equations.
Grouping variables.
Mm-hmm.
Okay, my curiosity is piqued.
Good.
Before we dive into that, though,
Yeah.
let's summarize what we've learned about graph search.
Good idea. It's important to consolidate before moving on.
Right.
What are your key takeaways so far?
Well, we saw how to translate equations into a graph. Variables as cities, equations as roads. Then we used DFS, our trusty navigator, to find the route representing the answer to our query.
Exactly. And what stood out to you about the efficiency of this approach?
It seems pretty efficient, especially with that visited marking to prevent loops. But I can imagine if the graph gets really huge and dense, DFS might still take a while to search through every path.
Excellent observation. That's where union find sometimes has an edge.
Oh, really?
It can be super fast.
Okay.
Especially when dealing with many queries about variables that are already closely related.
Okay.
Because those leaderboard lookups are super fast.
Okay, now I'm even more curious about this union find thing.
Okay.
Ready to venture into that territory.
Absolutely. Let's switch gears and explore how this family-oriented approach tackles evaluate division.
Okay, union find.
Yeah.
It sounds like something out of a sci-fi movie.
Right.
Like variables forming alliances to solve equations. But seriously, how does this grouping idea actually help us calculate those ratios?
Well, imagine each variable starts off in its own little club, kind of like a solo team.
Okay.
Then, as we see equations connecting them, we start merging those clubs together.
So if we have A, B, then A and B join the same club.
Exactly. And each club has a designated leader, the representative of that group.
Okay.
We keep track of how each member relates to the leader in terms of value.
I'm trying to visualize this.
Yeah.
So when clubs merge, it's not just about grouping, it's also about figuring out how everyone relates to the new leader.
Right.
That's pretty intricate.
It is. Think of it like each club having a leaderboard showing how valuable each member is compared to the leader.
Okay, that leaderboard analogy helpful. Can we go back to our example with A, B, B, 2, B, C equal 3 and C, D equal 4?
Yeah.
How would union find tackle that?
Sure. Initially, we have 4 solo clubs,
Okay.
A, B, C, and D, each with a value of 1 on their own leaderboard, since they're the leaders of themselves.
Right. 4 independent variables, each starting with their own value.
Yeah.
Makes sense.
Now let's process A, B, 2.
Okay.
Since B is the denominator,
Yeah.
A joins B's club. Now B is the leader, and A gets a value of 2 on the leaderboard because A equals 2B.
Okay. Club merger successful.
Right.
What happens when we add BCC of 3?
Now things get interesting. B's club, which now includes A, merges with C's club.
Okay.
C becomes the new leader.
So now it's a 3-member club with C at the top.
Yeah.
But what about those leaderboards?
Time for adjustments.
Okay.
Since B equals 3C,
Yeah.
B gets a value of 3 on the new leaderboard. But remember, A was already in B's club with a value of 2 relative to B.
So to figure out A's value relative to the new leader C, we have to combine those relationships, right?
Exactly. It's like a chain reaction.
Okay.
A 2B and B equals 3C. So A equals 2, 3C.
Yeah.
Which means A equals 6C.
Okay.
A gets a value of 6 on the leaderboard under C.
Wow. I'm seeing the elegance here.
Yeah.
Each merger automatically updates the relationships between all the members.
And finally, we process CDDOK. Osti's club merges with Odd's club, with D becoming the final leader.
Okay.
We adjust the leaderboard one last time.
Yeah.
And now we have one big club with D at the top.
Yeah.
And A, B, and C all having values relative to D.
Okay, the mega club is formed.
Right.
So if a query asks for a D, we just peek at the leaderboard and see A's value relative to D,
exactly,
which we already calculated as 6.
Precisely. No need to search through paths like in graph search.
Right.
It's all pre-computed in the leaderboard.
Okay.
And if 2 variables are in different clubs, we know there's no solution.
Okay.
Just like with DFS.
Now that's efficient.
Yeah.
But I have to admit, Union Find is making my brain work harder than graph search. It's powerful, but it takes a bit more effort to wrap my head around.
You're not alone. It's definitely more conceptually challenging.
Yeah.
But once you grasp it, it can be a real asset in coding interviews.
Right.
Interviewers love to see candidates who understand these less intuitive approaches.
Plus, it's always satisfying to crack a tough problem.
Absolutely.
So looking back at both solutions,
Yeah.
how would you compare their strengths and weaknesses?
Okay.
What are the key takeaways for our listeners prepping for those interviews?
Great question. Graph search with DFS is very visual and often easier to explain.
Okay.
It shines when the graph isn't too dense.
Okay.
Meaning there aren't a ton of connections between variables.
Right, like a map with clear, distinct routes between cities.
Yeah.
But if the map is a tangled mess,
Yeah,
DFS might get lost in the back alleys.
exactly. That's where Union Find shines.
Okay.
It excels when we have many queries about variables that are already closely related.
Okay.
Because those leaderboard lookups are super fast.
It's like having a cheat sheet.
Right.
But you did mention Union Find can be conceptually trickier.
Yes, mastering those club merges and leaderboard investments takes practice.
Right.
But if you can explain it clearly and confidently,
Yeah.
it really demonstrates a deeper understanding of algorithms and data structures.
Okay, so knowing both approaches and being able to articulate their trade-offs is key.
Yeah.
It's like having different tools in your coding toolbox.
Yeah.
Choosing the right one for the job.
Perfectly put. And remember, the more you practice these problems, the more intuitive they become.
Right.
Don't just memorize the steps.
Yeah.
Try to understand the underlying logic and why these approaches work.
That's great advice.
Yeah.
So we've covered a lot of ground today on evaluate division.
Yeah.
We started with the problem itself,
Uh-huh.
then tackled brute force,
Right.
and finally explored two elegant solutions,
Mm-hmm.
graph search with DFS and the intriguing Union Find.
And we've highlighted those key takeaways for acing those coding interviews.
Yes.
It's not just about solving the problem.
Right.
It's about demonstrating your understanding of the concepts and trade-offs.
Exactly. Well, this has been another deep dive on AI.Code.Cast. Hope you found this breakdown helpful.
Thanks for having me. And to all you listeners out there, keep practicing, keep learning, and good luck with those interviews.
We'll catch you in the next episode.